Hello.
Yes, sir, audible.
Is my screen visible?
Yes, sir, visible.
Yeah, I assume this. Yeah, I assume this screen is visible. My screen is visible. Um,
Yes, sir. Allah is introduction. Yes, sir. Some voice problem, sir. Not audio.
Technical issue.
yeah, this is introduction about me, but anyway, so I'm maybe a short one. I let me keep. So I work as RF
The
analog
voice is not
design
audible.
manager at Sykatiya Technologies. Let me sorry, your voice is not audible. Sorry.
There's some fluctuation in voice, sir. I think sound problem, sir.
Hello. No. No.
So volume not there.
Sir, I think you can increase your volume. Sir.
Hello.
Yes, sir, now audible. Sir.
Hope now it is better. Okay. Okay, let me start sharing my screen. So let me jump through the contents for this presentation. So let me introduce the analog IC and how it is used and what is analog IC, and through some example, and the trends in the analog IC design, how the we talk about technology shrinking and all. So those are the trends, how it goes and how it came so far, and the IC analog IC design flow. So this is quite an interesting part where I'm going to explain about how in industry they do the analog IC design. So what is the flow they are following and how many steps are there, and little bit of future for the analog. So let me start with an introduction. So what is analog IC design? So it is a successful implementation of analog circuits and systems using IC technology. So IC is an integrated circuit technology, and where we have multiple functions in one chipset. So an example for a function, we could say, simply if we can take a clock generator. So many of us know a 555 clock generator, right? So that is a simple circuit, but in a complex circuits, say a mobile phone, it requires a clean clock. So that the generation of a clock itself is a big task. So that is a simple function where we implement that with an analog design. So application of this clock will be mobile handset. So any device if you take, a clock is must. So ICs, the integrated circuits provides a single stop solution. So one analogy where we could relate this is, let's assume multiple grocery shop versus one supermarket. So multiple grocery shop, we go to every shop and buy different things. But in one supermarket, we go everything in one place. So that is the concept of integrated circuit. So we have multiple functions in one chip solution. So that is the ultimate goal of the chip makers. So as a manufacturer, so I will, so for example, we have a mobile phone. So in these days, these mobile phones will have camera, a GPS. So earlier days, mobile phone is just for making a call. So we are looking for multiple solutions in one handset. So that is what the, as a manufacturer, they will be looking for a one chip solution. So it must be making of all the functions. So that is the ultimate goal. But so the idea for that is the reduced effort. So let's assume, say, uh, let's say Apple is selling an iPhone, right? So inside there are a lot of chips inside it. So ultimately his aim is to buy one chip and put it there where it works seamlessly. But unfortunately that is not the case in these days, right? So that is a reduced effort and reduced bill of material. So the cost for the company, if you buy hundreds of chips, each chips cost $1. So it will, a device will cost $100 for the manufacturer itself. So instead, if you try to give the complete solution, so say $70 or something, so $30 cost for one device. So if you calculate for millions of device where in the manufacturing process, so here the company saves a lot of money. So that is the idea where the integrated circuit technology was booming. So let me take a familiar example. So almost everyone know. So this is an iPhone 11. So the reason why I take iPhone 11 is that I have worked in this project. I have designed a PLL, phase lock loop, for the GNSS application for this iPhone 11. So as a remembrance, I just took this picture. So as a consumer, we are most concerned about the look, feel, and how the functionality of this phone behaves. Right? So let's, for example, we take the camera and we take how fast the device is. But as an engineer, we are more curious about how the iPhone looks inside. Right? So let me give you, if you tear this iPhone and take what is inside the chip, so it will look like this. So it has got multiple ICs. If you could see, these multiple chips forms an iPhone. Right? So if you take a look at it, it requires more area, right? More effort to integrate all ICs to make one single application as a mobile phone. So integration is not an easy task. Let's say A13, they have mentioned that is an Apple chip, and there are multiple companies working for Apple, NXP, Cypress, Skyworks, Avago, Murata, and every company has a part in it. So TI, Texas Instruments has given a battery and power management systems similarly, so on. So if I were an Apple system engineer, I would want one single chip, right, which does the all functions instead of having all these things. Just put one, and that is done. But it is not that simple. Right? If you carefully notice the size of Nokia 3310, it's an old model, and iPhone 11, it looks almost similar, but iPhone 11 offers enormous features that Nokia is not providing. So how could it be possible? So we try to shrink the technology and implement as many functions into one IC. So that is the goal where we are traveling. So we want to put a lot of solutions there. For example, let me give another example. So this Apple PMU is Power Management Unit. So what is Power Management Unit? This will be the master for all the circuits. It provides the power. So it has a DC-DC converter, LDO, DGR, and supply monitor level system. So this is called one system, PMIC system, which is Power Management IC. So it is one example. This is a very larger picture of how it looks like, but it actually, so to explain you how complex it is. So this LDO will take one engineer to work and one layout engineer to work. So it takes approximately 2 to 3 weeks for the design and 1 to 2 weeks for layout and post layout, so on. So this DC-DC converter is a big circuit then. So assume this one small thing consumes one engineer and it has a lot of chips. So it requires a lot of engineers to be worked on. So this PMIC, why I have taken is this is an analog circuit, complete DC-DC, LDO, BGR. BGR is band gap reference. This is a low dropout regulator and supply monitor and level shifters. So, so the unique feature of analog IC is generally in an application, a major portion is occupied by digital. Let me give you another example how a function looks like in a short while. So approximately 80% of area is digital. So only 20% is analog. But the beauty of this analog is it takes 80% of the time for the design compared to the digital. So this is due to its complexity and it is designed from the circuit level. So that is the beauty and the contrast between these two pie charts. So let me give you one example. So there is a function called GNSS, Global Navigation Satellite System. So where you take your mobile phone and it tells you where the location is, the blue dot in your mobile phone, right, in the maps. So that is the function of the GNSS chip. It's a Global Navigation Satellite System. So it has analog. So how it tracks the location? So it takes signals from the satellites and it amplifies the signal and it gives to the digital portion. So the external world is analog. Internally, we process it in digital. So we need an analog to receive the signal. Right? So this is the GNS chip layout. GNSS is one of the function in the whole phone. Okay, so I have showed you multiple chips. So this is one of the chip, GNSS. So if you see, it is GNSS AFE. AFE is analog front end. So you see a lot of round things here, and there's a RAM, flash, and the Genesis IC, and MCU. It's a core unit. So if you see multiple rounds, right, these are all inductors. Right? So we might have seen inductors in the lab, which is very bulky. but in ICs we implement the inductor inside. So have you ever wondered, have you ever came across a crosstalk function? Let's say two systems working in the same frequency, right? So you are not able to receive that signal. Let's say I'm talking in some frequency, and there is same frequency with the noise in the outside. You may not be able to hear my voice. So that is the problem when you have multiple frequencies in a chip. So each inductor talks to each other. So that is a very difficult and complex part while integrating all the inductors in a chip. Okay, so the major challenge here is coupling. Coupling meaning, so if two lines are uh, flowing together. So let's assume we see a electric cable which is uh, all over the place. So if two lines come to across, it may create some kind of spark. So that is because of coupling effect. So when you bring closer, so it forms a capacitor, right? So that capacitor comes into a circuit itself. So that is the complexity of this. So in this picture, if you take, this is the analog portion. The blue color highlighted is the analog portion. Rest are all digital. So now you could see this contributes approximately 20% and rest contributes 80%, right? Approximately this. So the design time for this is almost 80%. So that these are the challenges. So that is that the analog takes, and each are taken from the circuit level. Okay, and one more strange thing, strange and it's the most toughest thing is the path for success is 2 to 3 times for analog. Meaning, when you do a chip, uh, let's assume this whole blue color, the marked Genesis AFE. If you do this chip, it takes 2 iterations for you to make it work. But for digital, it is 1 iteration. The reason behind it is 2 to 3 for analog is there are many factors which we may not be able to think, which is beyond our imagination. Say, if these two inductors are placed together, and if it is placed a little bit further, so we need to understand all these kind of effects. So nowadays the software are available, so which can tell the effect of placement of the inductors, but still it takes 2 to 3 passes for the analog to make it work. So that is the complexity the analog has. So this picture would have given you very good idea about how much portion. If you take any function, this remains the case. So let me give you an eggshell analogy. So what is an eggshell analogy is to show the importance of analog in any application. Eggshell analogy is used. Take any outer shell, it is analog. For example, physical sensor actuators. So everything is analog. Sensor is an analog. So where you, let's example, you have a pressure sensor and you press it. So it takes a signal in forms of current in the analog form. It is not 1 or 0. So but it takes in terms of so let's assume you have a mobile phone and you have a touch screen. So the touch screen, how it knows whether you're touching this place is because of the capacitors. So that capacitor is not binary, right? It won't tell 1 or 0, but it will tell you how much you are pressing into it. So which means so if you press harder, and the amount of amplification it inside happens is different, and if you press lighter it is different. So if your word comes amplification word comes, it is an analog, right? So you receive also, you have a FM receiver where you receive FM different stations, so that is analog. So everything over the air is analog. So if you take any kind of media or any kind of application, analog is a must. So inside sits the VLSI digital system. So analog interacts with the external world. So earlier meaning a few decades back, the digital analog was dominating a lot. Like all the systems were analog. So there used to be a huge devices. Now when the digital comes in, so all these start shrunk. So the system becomes smaller and smaller, but the functions are bigger. Still, analog is plays a vital role. So this is an eggshell analogy. So now let me tell you about the trends in analog design. So what do we call trends? So what is technology? Technology. What do you mean? So we say technology shrinks in the in semiconductor industry. Okay? So this is, for example, this is a MOSFET where it has a source, gate, and drain. So it has two parameters to play with. One is width and one is length. So length, what do we mean by is the gate, the length of the gate, and width is width of the gate. So this is where we start playing around. Okay. So what technology means is we start playing around the length of the device. So in 1971, earlier, so when MOSFET was introduced, the length of the gate was 10 micrometer. Okay, length of the gate. So as time passes, so it became 1 micron, 180 nano, and that 130, 65, 32. At present, the recent innovation is at 2 nanometer. So which means 2 nanometer, you can even imagine 10 micrometer itself. It's like a hair thickness, but 2 nanometers even smaller. Right. So the technology, how it shrinks is in the manufacturing industry. They need to be capable of doing this smallest length. Right. We can design anything, but the challenge lies in the manufacturing industry. So let's assume mm, you have a ballpoint pen. If you have been asked to draw a line with a scale, and you see some kind of thickness there, right? Let's assume that is 1 mm thickness. If someone asked you to reduce the thickness of that, how could you do it? So you will make the needle sharper and sharper, right? So that makes a half mm. But even if you want to go smaller and smaller, so that is the challenge in the industry. So now industry is coping up making very very finest, uh, uh, let's say it's in terms of sharpness. Right? So that is the level we are going. So at present it is 2 nanometer where IBM unveils world's first 2 nanometer chip technology. So that is the reason we shrink. So we are now trying to shrink the length. Why we are doing this? Why we want to shrink this length? So why we shrink the technology is one is the size. So again, I would like to take example as a mobile phone. So 8 years back, how the mobile phone felt in our hands. It was bulky. It is more like a half brick size. But now, if you could see, it is the most thinnest. Right? So we want to make things smaller and smaller wherever possible. So that is the reason we want to reduce the size. So an example, if you go somewhere and if you let's say I don't know which analogy should I take. So maybe I would take the dosa analogy. If you order a family dosa, it is costlier, and if you order one single dosa, it's a bit cheaper. But as in industry, they so everyone in the industry they want to have the cost of the material as low as possible because it is a competitive industry. So if you sell the product for $10, the other person sells for $8. Obviously, we would go for $8 product. So everyone would like to shrink the technology so that we benefit from that in terms of cost. And the second thing is speed. So the gate length, as the gate length shrinks, the the speed of the devices become faster because the capacitance, the parasitic capacitance in the gate is very less, becoming less and less. So the speed of the device will get faster. So earlier the phones were very slow, if you may notice, but now it's blazing faster. If any one of you had a chance to use a recent like a Samsung high-end series or the Apple 13 Pro or 14, you could see that the phone is blazing fast because of this shrink in the technology, because we could achieve the fast. So this is the trends in CMOS technology. So complementary metal oxide semiconductors. So as the year passes, so earlier the supply voltage was 3 volts for the desktop systems and portable devices for 2.5 volt. So each battery in our mobile phone can provide 5 volt supply. And the chip inside, so in this case 1995, chip inside the mobile phone needs 2.5 volt. So when the battery drains from 5 volt to 2.5 volts, so it will work till 2.5 volts. So after that, the system will die off soon. But as the year passes, we try to shrink the technology. So the supply voltage is becoming lower and lower, which is sub 1 volt for the portable device. So what is the meaning of this reduction in the technologies? You have 5 volt and a battery, and your system is 1 volt. So the battery start draining from 5 volt and 4 volt and 3 volt and 2 volt and 1 volt. So in compared to 2.5 volt, we have achieved 1.5 volt better than the previous thing. Right? So that is an improvement. Like we have a longer battery life. So that is one of the improvement for the feature when we reduce shrink the technology. And this graph shows about the threshold voltage and the power supply. Threshold voltage is when a MOSFET will turn on only when there is enough voltage at the gate. Right? So this is a graph comparing how the channel length. So if the length start reducing, the supply will also reduce and the VT will also reduce. So this is what the uh, faster device means. When you have a lesser VT, the device will be faster. And what is innovation in analog IC design? So we have this graph says in mid 1950, between 1950 and 1960, there was discrete transistors was invented, right? And after that, there was no invention till mid between 1960 and 70. So after that, there was introduction of bipolar devices. So till around 1980, bipolar were used. So if you check the older books, like 15 years old, so all the examples are with bipolar because earlier it was all bipolar devices. Right? So most of the descriptions would be on the bipolar. So after the invention of MOS devices, till now, till now, I think it was very strong and it plays a very vital role till now. There was no recent days there were many other um, inventions, but it is mostly on the material side. Like if we use metal oxide semiconductors in terms of silicon or gallium arsenide. So in terms of material, they are giving inventions, but the MOS basics remains the same. Now in recent days, it is FinFET. Again, it is a MOSFET again. So where we have a fins instead of gate. So that is the innovation in analog design. What do we how do we define innovation in terms of analog IC? So for technology driven, there are two terminology we could say. One is technology driven, and another is application driven. So for technology driven, we can take one example as cellular function. Right? It is there for generation, but it is done in new technology. Meaning, so you see, iPhones are there for years. iPhone starts from 3, 4, 5, 6, 7, right? So the phone is there, but what changes is they change the technology how they design it. So like I said earlier, they would have done with length of 10 micro. Now they are working in 5 nanometer. So but the function remains the same. So innovation in terms of technology, same call we are doing. Or even 20 years back, the phone does the same function. It makes a call, and now we could able to make the call as well. So, but the recent innovation is on the technology side. We shrink the length. So, and another, for example of an application driven is you see one technology. Let's assume we take, I talk about technology is the length, where which length we are using and which foundry we are using. So we say we use one technology, 28 nanometer, let's assume, and finding new applications like smartwatch, health tracking bands, and many wearables, what we are having right now. So these are the two things in terms of innovation. So this is being followed in the industry widely. And so this is the a simple diagram like explains. So what is innovation? So innovative solution, new technology, but a generic function is also an innovative solution, but a standard technology. But if you invent a new application for it, like I said, the smartwatches were invented like recently. It was boomed like recently. Recently meaning it was 5 years or 6 years back. But earlier it was not there. So that is one kind of application driven innovation. Okay. Just give me a moment. Let me take some water. So now let me share I analog IC design flow. So how we do the analog ICs, and it is very quite interesting. And this exactly is what being done in the industry. So this is very interesting part where you could see what the industry people are doing. So yeah, this is a flow chart. Uh, so this is a very detailed flow chart. So what it is, so I have written here about the analog design. So the format for digital design is a bit different, but I'm going to talk about analog IC design to how it starts and how it ends. Okay. So let's say we initially get some concept or an idea. So who makes the idea, right? That is called system engineer or a manager of team. So both collaborates and comes with an idea. So an idea is like let me take you can take any, you can assume anything, say mobile phone. So I keep talking about mobile phone because that is more generic and more easy to grasp. So this concept or idea of creating a mobile phone, it's been done by a system engineer. So every company will have a team of system engineers. So they know what the market requires and what needs to be given to the market and what kind of um, product will be hit. So that is called concept or idea. Then once the concept is being developed, we need to develop a specification for that. So this is the concept. Okay, so let me take one example of amplifier. So a requirement is amplify difference of two signals. Let's assume there are two signals coming in. So we need to amplify the difference of these two signals. That is one requirement. So that is called uh, concept derivation. And here, let me take an example as an op-amp or the concept. So the specification is, what are the specifications? So you know you need to amplify these two signals. But what are the specifications to design an op-amp? One is gain, bandwidth, and supply. So what is the gain? So how much you want to amplify? You want to amplify 100 times or 10 times or 50 times, that you need to define. So that comes under specification definition. The gain, bandwidth. So let's assume you have 1 hertz signal and you have 100 megahertz signal. So how much your system has to support? 1 megahertz is enough or 100 megahertz is enough. That is called bandwidth. And supply. And what supply you're going to design. So this is a very basic example. There are many other things follows, but just for the understanding, I would like to give. This is how the specification definition comes. So these two has been done by uh, the system engineers and the specification the managers. And then comes So these numbers 1 to 2 weeks, 3 to 2 weeks, it's a rough example, right, for us. Let's assume for a small block. This is not for a whole chip. I have given example of LDO or DC-DC converters, right? This is a very small part. This timeline. Please don't assume it as a full mobile phone. So full modem chip, it takes 3 years to develop a complete modem chip from the client, from the um, party to the customer. It reaches approximately 3 years it takes, because it's very complex system modem. So this example is for one simple system, like an assume like a DC-DC converter or LDO or a BGR. So now comes the architecture and block definition that is being collaboratively done by an analog designer and the manager. So what kind of architecture we are going to do, whether it is a single stage or a dual stage, or how many stages it requires, and what kind of block. So you are going to amplify difference of two signals. So what are the blocks required for that amplification? And you one op amp is enough, or two op amps, or how much gain do you need? So those kind of architecture based, right? So that is called architecture and block definition. And then comes the schematic design. So um, the analog engineer is fully involved in the schematic design and the simulation. So what is schematic design? So we have an idea. Let's assume I'm going to design an op amp. This is the schematic design. So this is how a simple schematic looks like. So you want to implement your idea and see whether it works or not. So for that, there are two separate things. One is the schematic, one is a layout. Layout is a real uh, idea that goes for the manufacturing. But before the layout, you want to implement the MOSFETs and see whether your idea really works. So this will be very close to the real one. The models will be written in such a way that it is closer to the post layout things, very close, but not exactly close, but closer to it. So that is being done by the circuit designer. So what are the process involved in circuit design? One is circuit, the topology selection. Let's say this is a two-stage op amp. So here we have a cascode, telescopic cascode, or a single stage is enough, or a cascode amplifier is required. So that topology selection is involved in the schematic design. So once you come to a topology selection, the picture shown here is a two-stage amplifier. And after that, there comes the device dimension. So what is the dimension of this device, M1, M2, M3, M4? So that um, that comes the real design of this op amp. So, and simple example is like a house plan. When we construct a house, we have a 2D plan of a house, but that's not a real house. So when you start constructing, you face a lot of other problems. So the plan, it will be there. So this plan, everything works. We identify and we verify the plan. So everything works fine. Everything is cool. So that is called the schematic. It is an analogy to make it up. So then comes the simulation part. Once the circuit is designed, and this schematic design, it does involves a lot of mathematical calculation. It does not directly depends on the tool. We do a mathematical calculation and we implement it in the circuit in the tool. Tool is just for verification of what our idea is. And then comes the simulation. So what is simulation? Simulation is, so let's say you there are multiple foundries, TSMC, global foundries. For example, we can take these two foundries. So if you're going to give your chip to global foundries, they have a different set of rules for their manufacturing. And if you go to TSMC, they have a different set of rules. Okay. So how do you verify those rules? So you get a model file, technology file from the foundry. Say TSMC will give you a foundry file and global foundries will give you a separate foundry file. So when you start designing this schematic, you use that model file to simulate how this circuit behaves. So this simple structure, which I have shown you earlier, behaves differently in two different technologies. A TSMC model file, it will behave differently. Differently meaning there will be changes in the the output. So in global foundries, it will behave differently. So in which technology are we going to fabricate this device? That is the prerequisite. So once we get the model file, it is being used for the simulation. So this is called simulation. So what are the simulation we do for an op-amp? Open loop differential gain, small signal bandwidth, output swing, how much swing it can withstand. So as I said, you have 1 millivolt peak to peak signal. You want 10 times of gain. So the output is going to become 10 millivolt peak to peak. So whether your system can withstand that 10 millivolt peak to peak, that is a requirement. And then power consumption, how much power this circuit takes. And there is one more term called common mode rejection ratio and offset voltage mismatch. For example, if we take one op-amp, we need to do all these uh, 7 kind of simulations to validate that op-amp. So this is the complexity of this analog design. So you do it and you do multiple analysis to make sure that the system does not fail. That is called simulation. So once you verify the simulation, if there is a problem, it does not meet your specification, then you go to the schematic design. Then you change, you simulate. So it is an iterative process. It takes a while for the designer to complete it by meeting the specification. So once it is ready, uh, the layout engineer. So these many engineers are required for analog design: system engineer, analog engineer, layout, fab, foundry guys, the test and validation verification engineer. So next, once this simulation, so this takes 3 to 6 weeks. For depends on the complexity of the design. So once it is done, it will be provided to the layout generation. So what is layout generation? Once your idea is ready and it is like start constructing a house. So what they do, the real they will face how the fabrication is going to be. That is called layout generation, and it is being done by a layout engineer. It usually takes few weeks, 1 to 3 weeks, depends on the complexity. So again, these are the process involved in the layout. So once the layout is, so let me show you how a layout looks like. So this is an example of how the previous circuit op-amp looks like in the layout. So here you could see the blue color or the gate length and width. So these are the real MOSFETs where we are going to give it to a foundry and ask them to fabricate a device like this. A layout engineer will do a DRC. DRC is a design rule check. TSMC will give you set of rules. So if these are the criteria met, let's say 2 lines should not cross each other. So that is one of the criteria from the TSMC, for example. And they give set of rules how to design layout. So once you do a layout, you do a DRC, design rule check. So each foundry will give you this design rule check. So we need to pass this design rule check. And then only they can guarantee the proper output. And what is LVS? LVS is layout as a schematic. So you do a schematic, and layout engineer do a layout. So each should match. So that simulation is called LVS, layout versus schematic. So this tool will check whether the layout matches, the connections and the device sizes are matching with the schematic. So everything is okay, then it is passed. This is called post layout extraction, PEX. So what is PEX? So in the schematic simulation, you will run the models, but here it exactly extracts the parasitics. So here in the schematic, you don't know these 2 lines. For example, the lighter green on the left top are passing together. So that is not being visualized in the schematic, but in the real layer, so it will extract all the parasitic capacitances. So and it will throw you 1.5, and which we will run it. So that is called post layout simulation. So once this is also iterative process. If your DRC is meeting, then you go to the layout generation, and again you correct it and do the DRC. And then next step is the LVS, and then next is the antenna rules. It is one of the rules. for connecting the longest string. And next comes the flex. So the layout engineer will extract and give the extracted file to you. So again, the analog engineer comes and do the post layout simulation. What is post layout simulation? So we have the extracted file and we do the simulation and we see whether this matches with the schematic results. So in schematic, it is your idea, but in text, it is an extracted from the real circuit. So whether these two matches, of course, it is not going to match because that is a real case, that is a model file. So if it is meeting the specification, then it is fine. Otherwise, we all together need to follow from the schematic design. Okay, so all this process will be followed. If the post layout fails, then again the engineer starts from the schematic design. What is wrong, and again you need to change. Again you need to run the simulation, and the layout engineer again changes the layout, and he runs all the rules, and then we give the post layout extraction. So this is the complete cycle. Again, it has to be done if it does not follow. Okay, and then comes the floor plan. So once your things are done, once okay everything is meeting, then next moves to the floor plan. So what is the floor plan? Okay, this is the post layer simulation where I have mentioned earlier, where it has a parasitic capacitance between these two lines, which is being extracted in the extraction file, which is not seen in the model. So next comes the floor plan. So what is a floor plan? So this is inside is a small chip function, and externally all are pads. Let's say let's see the 225 timer ICs. So it has an external pin. Right? So these are the external pins, the bluer ones outside. All the rectangular ones are the pads, and inside it there is a function. So how to place this chip, whether close to this one of the pin or close to the other pin, how an input output comes. So next comes this picture. Okay, this is called the chip floor plan. How the supply is being connected, and there are many other things. This generally requires a discussion among the team, and it is being done. So if you see it on the right side, these two looks like a input to this block. So the block has to be placed very close to the input. Where if you have some kind of input restriction, then you need to make it closer to the input block. So these are called the floor plan things. And then comes the dummy filling. So in the previous picture, you have seen a lot of empty spaces, right? So the dummy filling is also one of the procedures. So this is a very may not be very obvious, but it is very important step in the layout process. So once this has been done, the empty places has to be filled with some dummies. So because in the manufacturing process, the empty places cannot manufacture empty place. So process is called dummy filling. Okay. So an example of this is the left side is the before dummy filling, and right side after a dummy has been filled. Dummy meaning does not have any function. But should I give you an example? Yeah. So let's assume the manufacturing process is like a printing machine. Okay. So if you leave empty spaces, it is very difficult for the printing machine to print from one place to one place. So you need to give some kind of dummy things in between so that the printing does not um, break up. So it's a big chapter that we need to deal with. It comes under the manufacturing processes. So then everything is done. So this dummy DRC, dummy filling, and again they'll do the DRC for the whole chip. And this export to .gds file. So what they do is they export this GDS file to the manufacturer. So till this layout engineer will do. So all has been done. So in terms of manufacturing thing, so the layout engineer will give a file format where the industry can understand and start designing. So in the industry, once you give the file, they won't check what the design is. So they just simply get the design and they check whether it meets their manufacturing criteria or not. So in that format is called GDS, .gds. So this is called GDS submission. This submission meaning we give it to the foundry. Okay, so once it goes for a foundry, it goes for a physical fabrication. So how a fabrication looks like. So this is the fabrication unit. So the person handling here is on the left top is the wafer. So below is the processed wafer. Okay. So what is a processed wafer? It looks like a 12-inch wafer. Okay. So so all the squares inside is called a die. A die meaning um, say you want to fabricate an LDO. That square is an LDO. So there are multiple LDOs inside this one wafer. So they cut it. So how you receive the packet? The received packet looks like the matchbox. So if you open the matchbox from the industry where you receive, the chip price looks like this, the top, bottom, right. So it is more or less a tip of a pencil, the size of tip of a pencil, depends on the functionality. But usually it looks this smaller. So each processed wafer can produce it depends. So it is millions or thousands or 10,000s of that. Okay. So each silicon wafer is cheaper. Say each 12-inch wafer would cost around $2,000 or something. But the manufacturing process is hefty. That makes the chip industry more complex and more costlier. So that is called the fabrication. So once the fabrication is done, so this chip comes to the lab, the chip die, whatever it mentioned, it comes to the lab. So we need to check it. Again, the process starts. So who does it? Test and verification engineer does it. So he tests the chip and the spec definition is there in the top section. So he confirms whether the game product matches with the spec. Again, that process is being done. If there is a failure, then again it goes to the redesign. And again it starts from the architecture and block definition. So how it failed and what it failed. That takes 2 to 3 weeks to analyze the chip. So now you may understand you got so before that let me give you how a lab measurement is being done. So this is how setup, a typical setup of a lab measurement. So this is oscilloscope, functional generator, clock generator, spectrum analyzer. So everything will be there. So this is the test board. So they test the chip thoroughly. And for example, if there is a failure in the chip, so altogether, 2 6 it took around 14. It took around what 6 months of the time to design one chip, right? Till it comes from the fabrication unit. So let's assume 6 months. So if there is a problem in the chip, then you go change the architecture. Again, it takes 4 to 5 months. So this cycle itself, it takes around uh, 1 plus years. If the first time is not possible. And then everything in the second iteration, if everything falls in, then the chip comes out successfully to the industry. So this is what earlier I mentioned. Analog takes 2 to 3 passes for the success, and digital takes 1 pass for the success. So that is the complexity of this analog IC design. Okay, I think this is the very detailed information about what is happening in the industry, and it covers all the real topics where each and small topics are also being introduced here. So this would give a lot of good idea about how the chip industry works. So what is the future of analog IC? So what is the future? Let's say creative circuit solution for desired performance continue to be part of VLSI digital system. The interference and noise, always be at the cutting edge of the performance. So these are the like background ideas that where we need to keep it. Let's say um, this is a large VLC system. Okay, so continue to be part of a large VLC system. So you need to make the chip function more larger and larger, right? More and so this is called interference and noise, meaning um, you have so definitely everyone would uh, have came across when you call a person, you might have landed to a different person. That is called interference or a noise where some of the other call might have landed to you. So thus, those are the challenges, and those need to be reduced. And always be at the cutting edge of the performance, meaning the performance is does matters, right? Now the device becomes faster and faster and more handy, and then the camera takes a very good picture. Those kind of things. Okay, mm, this is based on my uh, understanding about what analog skills required. What are the skills required for an analog designer to be an analog designer? So grasp multiple concepts simultaneously. So for example, earlier I would have shown you one picture where you have multiple indicators. So here you need to grasp multiple concepts. It is not about the designing inductor, but if you keep two inductors together, what happens? That is called multiple concepts. So you need to be able to grasp those concepts simultaneously. So appropriate simplifications and assumption. So maybe I should maybe if there is a chance I would show you how complex or big the system looks like. So I have shown you a schematic of 5 transistors, but actually there are millions of transistors in the design. So you cannot design a complex million transistor. So you need to make some kind of simplification and assumptions. So grasp of both modeling and technology. So how to model uh, a MOSFET or a function, and you need to have a broad skills. Uh, it is not only about circuit design, but many other skills you require for designing a neat one. So learn from the failure. So if you fail from one of the circuit designing, then you need to learn from that. Use the simulation correctly. So you have a tool. You should not use it like a magic wand. It won't work that way. So what happens is there is a common saying called simulation truths. Right? Usage of simulation into a common sense is a constant. Okay, um, so we need to use more common sense than use of a simulator. Simulator, some a few may end up doing iterations. You give one length and you check whether you meet the function in the simulator. It is not meeting. Then you change some different length. It is meeting. So that is called usage of simulator. But in common sense, we need to use the common sense. What is the problem in the circuit and how we rectify it? So that is the usage of common sense. So if we use it properly, we need to reduce the usage of simulator. And simulators are only good if you already know the answers. You need to know the answer before you start doing any kind of circuits. Otherwise, we will never be able to be design one. Okay, now it is I come to the last portion of the presentation. So there comes the opportunity in analog design. So first is artificial intelligence. Um, you may know now there are few courses being added to the um, education, like AI. It's a different uh, course. So that is the impact of AI it's being done. So AI is of course a software coded, but it does require a high performance hardware to be implemented. And next is autonomous driving. Example is a Tesla car. So where it is implementing Tesla, of course, BMW, Benz, Mercedes Benz, they're all implementing the autonomous driving, Volvo, everyone. So that there comes the analog IC. So it requires a lot and lots of analog functions in it. Next is an Internet of Things. Internet of Things, a fan now it is being operated from a mobile phone at home. So that is the beauty of IoT. That requires an uh, analog chip. Of course, it requires digital, but I'm just telling you where the analog still plays a key role. And then the blockchain technology, which requires high performance computing system. So this analog can provide high performance. So this is more towards the semiconductor industry itself. And then comes the 6G telecommunication. Now the research has been started on the 6G. Now we are in 5G era. And now the 6G era is going on topics. So these are the excellent opportunity. This is not limited to, but there are other opportunities as well. I just mentioned some. Um, so that is it from my side. And any Q&As, so that's all for the presentation from my side. So you are welcome to ask any questions, and I'm happy to discuss.
Queries may be raised now.
Sorry, I couldn't hear you clearly.
Questions can be asked now.
Could you please come again?
Hello, sir.
Hello, hi, Manish.
Hello, sir. Good evening, sir. This is Venish Kumar from Theni.
Hi, good evening.
I had one doubt, sir. It's actually your slides are very nice and it's so informative. And I had one doubt, that is any free tool which is available to design analog design, sir, analog circuits.
Yes, there are tools available.
Yes,
So I presume there is one more session tomorrow where
okay,
I would be giving an introduction about a small tool very effective for this analog design. Yeah, that is
okay,
free there.
okay. Thank you, sir.
That is called ALT Spice.
ALT space. Okay, fine, sir.
Yeah,
Okay, thank you, sir.
sure, welcome. Any other discussion points?
Kindly ask your questions.
Hi, Ashok Kumar, sure. So I believe no more questions.
Sir, I have only one question, sir.
Sure, hi, sure.
Yes, sir. Already we all the other three sessions we have heard about the IC 0 rupees and how to
Okay,
design a mask like that, sir.
okay.
Apart from that, any new information should be needed for a faculty to be a scholar, sir, or in this field, VLSI?
For a faculty, is it?
Yes, sir, for a faculty to be a scholar or PhD level or next level,
Okay,
sir. What should be we
okay,
to
okay.
update for our next level?
So I'm not sure I'm the right person to comment on it, but um, so we need to be. So let's assume the prerequisite for a PhD is like we know how to design an IC
Yes, sir.
yeah. So the next level, if we want to go to the PhD level, we need to identify the problems the current day is facing. So
Yes, sir.
if
But
you,
we have to go for papers, newspapers, or any magazine, like the
yes,
electronics for
ye-
you, like that, sir.
yes, sure.
So electronics for you,
So
one shop suggested me, sir. That's why I asked you.
yeah, they will give you, yeah, that is a very good website where they daily send you an updates on what is going on in the industry. But
Yes, sir.
to be more specific, we need to dive into one. You need to take one circuit with you for a PhD. That is my understanding. Like, for example, you can do a PhD in ADC, analog to digital converters, or PLLs. So you can
Yes,
take
sir.
one ADC and identify what is the problem and what is the your innovative solution to make it better, working better. So that kind of innovation is required for next level of PhD in terms of analog
Yes,
or
sir.
IC design. IC design. Yeah.
Yes, sir. But in
Yeah.
a P space is a tool, is a common tool for analog, sir. P space.
P-Spice, yes, it is for analog, but it more deals with the block level. You cannot do it in the MOSFET level in the P-Spice, I believe.
Yes, sir.
So
What should? Yes, sir.
you can put an op-amp, you can put
Upon.
an 555 timer in that P-Spice, but you don't know what is inside an op-amp. So
Yes,
you
sir.
need
Yes,
to
sir.
go one level below and see what is in the MOSFET level. So that
Okay.
I'm not sure P-Spice can be able to handle. So there is
Yes,
a
sir.
tool called LT Spice where you can.
It's
That is for
open source, sir.
basic. Yes, it is open source.
LT space. Yes, sir.
LT Spice. So tomorrow there is one more session is assigned. So I'm planning to give how it works, a general idea about how the tool works.
Okay, sir. Okay, sir. Thank you, sir.
Sure, welcome. Yeah, Balachandran has commented that session. Thank you, Balachandran. Thank you for your feedback.
On behalf of Department of ECE, MSAJCE, I take this opportunity to propose the word of thanks to our resource person, Mr. Karthik. We are enlightened with your knowledge and presence, sir. We thank our management, principal, and HOD ma'am for their support. With this, we will move on to the end of the session. The next session will start sharply on tomorrow at 10 a.m. Thank you.
Yeah, thank you for providing me a slot for explaining this, and it was great meeting you all. And then on the education side, it was nice meeting to you. Thank you everyone for their appreciations. Thank you.
Thank you, sir.
Thank you. Bye bye. Have a wonderful day.